Non-book has the honour to give you Tom McCullen.
That's me. So before I get started, could you, on a scale of 0 to 5, where 5 is you're basically rich, you're a total LabVIEW nerd, you know lots, and 0 is you've walked into the wrong room and you feel too awkward to leave. Where on the LabVIEW scale do you feel like you are?
Can we put like a minus in front of that, like a -3?
Feel free.
Oh, okay. Thank you, that's me then.
I squared.
Okay, so on 3, 1, 2, 3. Good. Okay. Okay. Right. I'm getting either 4s and 5s or 1s and 2s. Okay. All right. I'll tailor the presentation to suit. Okay, so I'm Tom McQuillan. I'm a senior software engineer with JKI. For those of you who don't know who JKI is, you might know of VIPM or the Karaya unit test framework that you were shown earlier. JKI developed both of those. JKI are an alliance partner based in California in the Bay Area. About me, if you don't know who I am, I'm a LabVIEW and test and architect, embedded systems developer, and LabVIEW champion. Basically means I'm a massive LabVIEW nerd.
You're a 6.
Yeah, thanks. I don't know if that's an insult actually. Okay. Out of 5, that's fine. Okay, so on this map, this is where we are. There we go. If we zoom out, this is the general area where I live. I won't give you my address. Then my colleagues are over here. This is San Francisco. In then the Bay Area, like Silicon Valley area. That's where all my customers basically are. Customers of JKI include companies like NASA and other aerospace and defense contractors and other American defense contractors, which I'm not allowed to work on. But I do work on plenty of other JKI projects in that sort of area. Okay, so I want to talk about a project which I'm working on, and I'm going to talk through this project, and along the way I'll identify why I think LabVIEW is amazing. Even at the end of the presentation, I'll talk about what we can expect, what's coming up, what could come up. So I'm working on a project, and this company needs to characterize a particular device. I won't go into too many details, but we need to characterize that device if it gets stabbed. Engineers tend to call this penetration testing. We need to characterize that device if it gets a surge over current testing. What's the next one? Fire. If that device overheats, what happens? The last one is a drop test. So what happens if we just drop it off a 5-story building onto a concrete floor? Well, all of these items, invoking these 4 tests on a particular device is very straightforward. They're all digital outputs that you can connect them to a relay if you need some extra oomph to get it going. We have there's NI piece of equipment and an external PSU. But it's not just about blowing up this device under test. We also need to get some data to characterize what happens to that dart. So I have a range of thermocouple strain gauges, general DIO, AIO. And this is all very straightforward. Just back in the hardware for this. You can use everyone's favorite configuration editor. And yeah, because I'm quite experienced at all of this, I knew that this is going to work. And I guess this is the first marvel that I want to talk about when it comes to using the NI ecosystem and LabVIEW. I know that I can buy this equipment in the ballpark range of 3,000 to 5,000 ish. I think that's in dollars. and it's going to work out the bag. It's going to be more performant than I need it to be. This project will just run on Windows. But the next, to go more specifically into this marvel, I'll talk about this DIO card. Probably the most basic card on there. It can either be on or off. But I need various I/O channels to drop the device, to penetrate a nail through the cell, do external shorts, surge, and I need other on-demand I/O for interlocks in the system. For temperature control, though, I also need to borrow a load of DIO for controlling heaters. I have 4 independent heaters on this DUT, and I need to be able to regulate the temperature around the DUT. DUT, device under test, DUT. And because the heater can either be on or off, my first thought was, okay, closed loop control circuit. If this is my set point, if I am below that set point, I can turn the heater on, and else I turn the heater off. And we end up with this, what we call a bang-bang control circuit, also called like a push and vent control circuit. We bang to a top threshold, and then we turn it off, we bang to the lower threshold, and we end up with this zigzag. That's fine, and this is our CV, what is CV? Control variable, out of the DIO. Now, that's all very well and good, but it doesn't look great, and when we're trying to characterize systems, we probably want more control than this. We want to make that tolerance as small as possible. And also, if you mess up your configuration for your tolerances, what tends to happen with a bang-bang control circuit like this is you have massive overshoots. Even though you've told your heater to turn off, that heater is still very hot. So that heater is going to continue to increase the temperature of your duct, and then the same thing happens in reverse. You told the heater to turn on here, but actually your duct is getting cooler and cooler because of the ramp rate of warming up your heater, and basically your duct is a heat sink. So we don't want that. Instead, we want something that looks like this, where we can start thinking about our heater not as a on-off true-false heater, but something that we can control on an analog scale. I want this heater to be 75% on. And then by adjusting our control variable, we can create a nice curve on our process variable, the true temperature reading of our duct. And we're smart here. You know that we're going with pulse width modulation for this, where we can play around with the duty cycle of the percentage of on time versus off time for our frequency. So all of this to say, I needed a way of implementing PWM with the hardware I already had. Now, when I got to this stage in the project, I was thinking, yeah, that's fine. This card, I'm sure it has counters. So I looked at the data sheet, nothing. I saw that this card could go up to maybe, 20 megahertz sample rate, but yeah, nothing about counters until I had to look at the data sheet of the chassis itself. And then I realised, bloody hell, there's 4 counters on the chassis, which I can then route through to the DIO. And if you're unfamiliar with what a counter is, it effectively lets us monitor frequencies, whether that's frequency generation or frequency monitoring. So I read through the data sheet of the chassis, because typically I work with PXI backplanes, so I was unfamiliar with what a CDAC chassis backplane sort of had to offer. and I saw, right, it has 4 counters, and those 4 counters I can filter through to my DIO as if that DIO card had those counters sort of inbuilt. The API was absolutely no different. And so yeah, this saved the day. So I guess adding on to the previous hardware wonder of LabVIEW, this was a wonderful moment for me, realizing I've got myself out of a hole. And I could implement a really nice control system. Now, that control system in LabVIEW, in G, looks something like this. I can't show the actual customer code on here, but effectively we have a set point. This is going to be a user-defined or a test-defined parameter. We have the process variable. This is a thermocouple reading near the heater. And then our control variable, this is controlling one of the counters I showed you on the chassis. And then we have our PID controller. Who here is familiar with PID controllers and closed-loop controllers in general? Okay, most of you are nodding. For those of you who aren't, basically we can take the difference between our set point, the thing we want the system to get to, and where the system actually is. We can summate them and then perform an algorithm to predict what the output should be. And so the output here is going to be a number between 0 and 100, where 100% duty cycle would be on, and 0% would be off, 50% would be your standard square wave. I'm using these functions here, here, and here to convert from real-life engineering units into a scale between 0 and 100. You don't have to have these here. You can enter into this function your ranges, but I prefer to scale everything to a percentage. It makes maths easier. So yeah, my mind works exactly like this. G-code in general is a wonder in LabVIEW. It gives me the ability to think of a problem. Then I'm very dyslexic, so I will, in my mind, just whilst I'm having a coffee, just maybe close my eyes and think through the solution via a graph in my mind, exploring different avenues until I get this solution I'm pretty sure will work, but I find it difficult to explain that solution to other people. And so I always end up just sketching it. In LabVIEW, you don't need to sketch it, you can just code it. And so this graph maps to how I think about problems. Another great wonder. Now, humble brag, I'm quite good at tuning PID control systems, but out of the box in LabVIEW, I don't know if it's limited to LabVIEW Pro or LabVIEW Base, but the PID functions come with auto-tuning capabilities. So I will ship the system to a customer having tuned it, and I'm pretty confident in it. But if they want to fine-tune it a bit more, you can enter a true Boolean into here, and then, hey presto, there's an auto-tuning wizard. And so I can ship that to the customer, basically no effort on my part, but it's improved their experience of my product. It's things like, there are loads and loads of things in LabVIEW like this, which elevate your customer's experience. Another great wonder. Okay, so yeah, going back to this slide, we've talked about how V's DIO is on-demand I/O. Then at the bottom here is going to be hardware timed. With the PWM signal I'm sending to the temperature control loop, that will be a standard 10 Hz signal, which I'm then adjusting the duty of. And because it's hardware timed, I know it's going to be pretty damn close to 10 Hz. It's not going to be controlled by Windows. What are we going to talk about? Yeah, so hardware timed, counter timed, and on demand or software. Now, everything that you see here can be controlled by exactly one API, DAQmx. Again, all feeding into how great it is to use NI hardware in LabVIEW. Yep, basically these 10 or so functions will do all of your tasks. Now, all of the code is going to basically look like this, except it isn't. Let me explain. All of the DAQmx code, you can create a channel, configure it, read or write, stop, clean up. And even if you don't have the hardware attached, you can simulate your hardware in Max. So again, this is great. Except for this particular project, I really wanted to be able to simulate devices to a higher degree than what Max gives us. Max being the Automation Explorer, which allows you to configure this stuff, the hardware. And so I basically took each of these functions and wrapped them into a special function which allowed me to swap the behavior depending on whether the hardware was connected or disconnected. And we call those special functions like dynamic dispatch. If you're familiar with object-oriented programming, great, you'll know what I'm talking about. If you're not familiar with it, it's a way of changing functionality based on conditions. Think of it as a fancy case structure. The way that object-oriented programming and dynamic dispatch implementation is implemented in LabVIEW is another great wonder. If you compare how you do object-oriented programming in C++, and you come to LabVIEW, you will feel like there are things missing. There are things you can do with programming in other languages that you can't do in LabVIEW, but I think that's okay. Because in LabVIEW, we have the data flow paradigm, which basically says that function won't execute until that function has, etc. downstream. And the additional benefits you get from OOP in other languages wouldn't fit that paradigm. But the way that this works, I think is really cool. You can double click on one of these fun functions and see which implementation, or see the code in each implementation. Okay, enough OOP. I've lost most of you, so I'll move on. Yeah, so we have this generic code thing. Who can tell me, how do we do multi-threaded programming in LabVIEW? Stick on a
Don't tie it together.
Perfect. Stick on a block diagram, don't tie it together. Great. So I can copy and paste these. So I have 1, 2, 3, 4, 5, 6 loops on this block diagram. Great. I have 6 threads that are all going to execute. Do that in C++. You know, I know a bit of C++. I know enough Rust in order to implement this, but I can do this in 15 minutes. The time it would take me to implement it in another language would be colossal. The cost for the customer of buying a LabVIEW license, whether that's LabVIEW Plus, the full suite of NI hardware, well, my development time, to be frank, far outweighs the cost of the hardware and the licenses. So if I was made to use free software and free programming language and cheaper hardware, the customer would pay 10 times the amount of programming hours. So yeah, multi-threading in LabVIEW, amazing. Those of you, who here was at GDevCon, the last one? 1, 2, 3, okay. My last GDevCon talk, I spoke about the LabVIEW compiler stack. I won't go into it here, but another wonder. Programming in LabVIEW is super quick. I don't think LabVIEW gets the recognition it should. As a programming language, LabVIEW is fast. LabVIEW can have a seat at the same table as programming languages like Rust. And it's down to the low-level virtual machine. It's in fact the same compiler technology that Rust uses. It's a different stack, don't get me wrong, but fundamentally the same technology. To prevent context, Python isn't in the same room as the table. Python is orders of magnitude slower. Okay, side note, that's great. LabVIEW's awesome. Next, LabVIEW Visa. One of my pieces of hardware couldn't, well, it was a PSU, that's not NI. This is the process I went through to learn, that's not DAQmx, how do I program it? Well, I Googled it. I got the model number, the programming manual, there's a PDF. Let's scroll down, okay, so I need to send this function, I get this reply. All right, so from that screenshot, from that datasheet, I took a screenshot of things like the baud rate, the serial setup stuff, and the message. Using Visa, I think, again, Visa is underrated in LabVIEW. The amount of effort it would take to keep up with a standard like Visa is colossal. I wrote this on the train up from London this morning. It didn't take me the full train journey, but the point is, this maybe took 5 minutes whilst on a shaky train, and that's going to work. Unit test it, but it's going to work. Small trick here, if you've, slight tangent, again, this is awesome. If you've specified your termination character and enabled your termination character, this function is going to wait until it's received a number of bytes or until that termination character is received. I see lots of people write the function, put a stall data flow of 200 milliseconds, and then use a read bytes at port, read. You don't need to do that. Specify termination characters. Also use Visa events. They're quite cool. I've used those a lot. This technique doesn't really work if your termination character is more than 1 character long. So again, NI Visa, this is awesome. You should use it. It's great. But you only need to use this if someone else hasn't already produced a package. So that comes along to another thing that's awesome in LabVIEW. And we're slowly getting into the realms of how the community builds a great programming language. This is VI Package Manager, created by JKI long before I joined the company. I won't take any credit. Apart from one new feature where if you're logged on and you need to license it for Pro, it will scrape your new serial number and enter it automatically. I did that this morning, it works. Yeah, so VI Package Manager, loads of packages here. It's the way that the community can share code, build it, publish it on the LabVIEW Tools Network or the VIPM, or just your local company repo. Send it. So this is great. What's not so great is saved versions in LabVIEW. Every year a new version comes out and you're like, do I upgrade all of my packages but then restrict other people from using them if they're using 2020, but I've updated everything to 2022. We're already at 2024. Q1 is released, right?
Yeah.
Yep. I'm playing around with the Q3 beta on my my laptop, and so where everyone has 2020, that's starting to get a bit old, even though everyone loves it. Okay, so let's say Abigail creates a package in 2020. Fiona wants to, it's open source, I want to contribute. Fiona can't because she's using 2022. If she touches that package, that upgrades everything to 2022, and I can't remember what's her name? Abigail. And then Abigail.
I've contributed something.
Then Abigail's going to see that and be like, nope, that pull request is blocked. So another great wonder in LabVIEW Q3, it was actually released in Q1, I believe, if you knew what you were doing. But it's more public now in Q3, is if you're creating a library that you want to distribute, right click, go to properties, general settings, you can have a new save in version. You can use LabVIEW 2024 and you can use Zoom and all the other great features, but your source code can be saved in 2020. So now Fiona and Abigail can program in different versions of LabVIEW, but they both get saved in 2020. If this is for a library, if you want to do it for a directory, put a .lv version text file in your directory, put the version you want, let's say 20.0. And now notice how this block diagram is 24Q3, but it's saved in 20.0. And so this is going to be great for the open source community in G, because now people can be using the latest version of LabVIEW and contribute to packages which are saved in older versions and keep them in their older versions. But this is all great for the version of LabVIEW, but LabVIEW needs to be configured to have different packages installed. Let's say Fiona built this package based on the OpenG variant library. They used that because it was a shortcut. It had some new controls they wanted to use. Well, to contribute to a package, or to contribute to an open source project, every developer's computer needs to have all of the dependencies installed. So one thing I've been working on with Kring is Dragon, JKI Dragon, where what Dragon will do, Dragon is sort of an add-on to LabVIEW. There's also a desktop standalone version. But what Dragon will do is scan your LabVIEW project. It will say, okay, you're using DAQmx. So everyone who uses this project needs DAQmx installed and the LabVIEW support for DAQmx. But this isn't variant. This is the OpenG configuration variant package, and Dragon was able to find all that's being used as well. And then it gets stored in your project. And on disk, all of that metadata gets stored as metadata in a .dragon folder, which you can hide if you want. But basically it means when you open up your LabVIEW project, we have the ability to install all of the required packages to work on that code. Let's have a look at this. So this is Dragon Desktop. This is how I now launch LabVIEW projects. You can see Jim did that. You can right-click a project and choose the LabVIEW version you want. Maybe a bit superfluous now that we have LabVIEW 24 Q3. But I now selected this project. It's going to open it in 24 because that's what I configured it to open it. It's now going to search, are all of the packages installed that were specified for this project? If no, then it will take you through a wizard to install all of your dependencies, or all of the required dependencies, and then open the LabVIEW project in your chosen LabVIEW version. I'm doing for time. Okay, speed up. So yeah, I'm super psyched because again, this is going to increase collaboration within the community. The Dragon isn't complete. there's more features I want to add to it, but Dragon is being shipped with LabVIEW now as part of the LabVIEW installer. You can install Dragon onto the LabVIEW toolbar. And Dragon all came about from an idea that we had in the LabVIEW community. And I guess this section of the presentation of the imagination of what's to come, as I was thinking through different ideas, they all came down to the community. The work that NI has been doing in recent months, and I guess when Nancy started her role, is to engage the community a lot more. The symbiotic relationship between NI and developers has changed significantly, or I've certainly become a lot more aware of it in the last few years. It used to be the symbiotic relationship was NI developed LabVIEW, and LabVIEW developers gave them money. But in order to be a great programming language, we need a symbiotic relationship where you essentially have a language owner, which is LabVIEW, and the LabVIEW community who will work with that company or owner and help them create a better tool. For LabVIEW to grow, it needs to be accessible to everyone. And tools like Dragon will help that. It will make working on tools more accessible. Community. So I brought up this slide earlier, but imagine in one of the streams that you could write G but have it run on bare metal programming, run on an FPGA. I know we have LabVIEW FPGA, but that uses a certain tool set that you have to use Rio. Imagine you buy just an off-the-shelf FPGA from Farnell, nothing to do with NI. Can you program it right now? No. As a community, could we make it work? Yes. The compiler stack in here, we have community expertise in how this works. We all write LabVIEW. We all know about the broken run arrow. If the pre-compiler says it's fine, you get an OK run arrow, else it gets broken. And then it does some optimizations. It then goes into low-level, sort of machine-level code, or IR, so we call it. But anyway, we can basically get to this stage, and then change what's in these boxes. Maybe we could transpile from G, which we program in LabVIEW, over to Rust. Then once we've got our G code actually transpiled into Rust, maybe we could put that code onto a microprocessor. There's a long way to go, but it's all in our imagination. That is actually in reality, not just in someone's imagination. We've proved this. Open sourcing parts of LabVIEW. Jono mentioned this earlier, but the VI icon editor is now open source, or is going to become open source in the process of. But although the VI icon editor will be great to be open source, there are a few bugs in it that my boss Jim is keen to just fix and push for everyone. This will set a precedent of making LabVIEW better, strengthen the trust, the relationship between NI and its users, and basically force NI to come up with better automation releases and tooling, such as Docker, as Jono mentioned earlier. And tools like, for those of you who aren't aware, Docker would be a way of, once you've committed your code to a big cloud somewhere, have that code download somewhere else, build, maybe do some tests, and then upload the build artifacts like an executable or installers somewhere else. The thing that downloads that code could be a UI-less system like Docker. But anyway, that relationship is also proven. Jim's got Docker working. Side note, I noticed this on the train. It's going to be fixed, but I thought it'd be interesting. I opened up the icon editor in 2024 Q3, and it came up with the original one written in C. You won't see this when it's actually released, but there you go. Let's talk about AI very quickly. By we, I mean JKI. AI enhanced searching. Now, I just put in a search term there for how do I manipulate a cluster? And it came back with a selection of VIs and packages. Now, this is something I actually needed that I didn't know existed. I was able to click on that specific VI. It gave me more information about this VI, and this isn't AI generated, this is just the VI details. But I can then see what's the owning package of that. We're like, oh, actually, yeah, that package contains a bunch of VIs that I want in my API. You can then install it through VIPM into LabVIEW. Give this a go. You get varying levels of success, but if you sort of know what you want the answer to be, then test it yourself that way. Don't just blindly walk into it. On that note, what about a GAI assistant? And I talked about Nigel. We can create also a community version. There are various technologies that exist in other programming languages which would be super cool if they existed in G. What if we had, I've put Clapey here, but a GAI assistant, or Gala, where you could either ask it a question or have this assistant be sort of self-aware. Oh, it looks like you're creating a messenger library. Would you like to create the type def you were talking about earlier for your state machine state transition? Or you've just dropped down a generate user event function. Well, I can see that in your data bus, there's a user event reference. Would you like me to unbundle that reference and wire it up? In there, we can train that AI. We can train that neural network with just a simple thumbs up, thumbs down. Yes, I want to do that. Or, nope, you're off the mark. You're not in the right context here. Or if we could ask it questions like, oh, could you create an icon for this VI? It might come back with saying, no, that functionality is not available yet. Would you like a feature request? You can give it a thumbs up. And again, we can give the AI model some training data that way. There's a whole bunch of things that we could do with Clippy, and I sort of want to steer away from I don't want to be talking to LabVIEW. I don't want a LabVIEW chatbot, like sort of similar to like ChatGPT. I don't want a question answer. I want an AI which is which captures the context of which I am working. Sort of like Copilot. If you've used Visual Studio and you're typing some Python and it gives you a suggestion of what the rest of the function should look like. And be like, oh yeah, enter. Imagine that in LabVIEW. That'd be great. Okay, I'll wrap this up. So working with Jim Kring as in the JK in JKI, he's been pushing a lot of these community initiatives. Firstly, we want to lower the entry into LabVIEW. So provide a simple one-step install for LabVIEW and make that installation fast. Installing LabVIEW at the moment is crap. It takes a long time because if you just blindly download LabVIEW, well, it actually downloads NIPM. It then gives that a command to download LabVIEW. But that aside, every optional extra is selected. So if you blindly click through, it's going to take you a day. What we need to do is basically remove those add-on modules. And the installer also contains many under the hood services. What we need is a installer which is just the core LabVIEW, in there we can accessorize around that. Older versions, what does that say? LabVIEW versioning issues solved, LabVIEW 24Q3, great. Move to a text-based source code for file formatting. This is possible, we've done it. Whether NI will make this the standard, I don't know, but this will open the community up to using greater tools that already exist out there. It's not as far-fetched as it might seem at first. What if we had super lightweight console applications? What if we had could write like Windows services in LabVIEW? Things that don't require a user interface, things that just run quietly. There may be a few kilobytes large, if that. LabVIEW into Docker, yeah, that's proven technology now. It's not being rolled out. Were you saying that NI is going to continue with that? That's great. Open source parts of LabVIEW, yeah, done. Well, almost. Once we set the precedent, and if we as a community make that a success, NI will open source. Like Eli is very keen for this to happen. If you're not subscribed to like Jim on create.vi, it's good. He's got interesting things to say. Have a look at what he's got there. But yeah, so in this presentation we went through how I think LabVIEW is great. It's just a couple of key things I came across recently when developing this project and what we can do to make LabVIEW even better as a community. All right, that's all for me. Thank you very much.
Thank you, Tom.